Well, here is the Einstein image with dots. These extrema points might be higher than the neighbors, but some of the extrema may not be higher enough, or it may not be very high. So we want to be sure that the contrast or the value is higher than particular amount, or in other words, we want to remove low contrast feature. For this, what we do is, if the magnitude of intensity in the difference of Gaussian image is less than certain value, let's say C, it's rejected. So we get the image here with the interest points which has a contrast value greater than C only, and the rest of the rest of the points are rejected. And sorry. And next thing we need to get rid of is we need to get rid of edges. The idea is to calculate two gradients at the key point, and both are perpendicular to each other, which represents the corner. And mathematically, this is achieved by the Hessian matrix. Using this matrix, we can check if a point is corner or not, or if it's edge, or it's just a flat region, which we have done in the Harris corner detector, where only corners were selected as a key point. Here are the images with the extrema points, and these are the only key points that don't include any kind of edges. So these are the image with extrema points without edges. And as we pull out all the extrema at all the different scales, so these are robust with respect to the scale, and this is the shift detector or scale invariant feature transform detector. And about the shift we will discuss in detail in subsequent slides. And as we have been talking about how to find interest points and how to detect them, and we talked about Harris operator and other kinds of ways to find them. Here, for example, we have got two pictures and finding where we find interest points, and in two images this is like about 500 points extracted, and with the Harris detector, and if we can see that there is a bunch of points found. And what is good is that a lot of points like here on the left side is also found in the right side. So one of the things we have been looking for is reliability. That is the point that we find in one image, that is the first image, should be found in the other. But now the question is, given that we found the points in two images, like in both of the image 1 and image 2, the question is how to match them. Like here we can see, like how can we match these points, and how to determine which point on the left image are same as the points in the right image or multiple images. So to do this, we need what's referred to as a descriptor, and a descriptor is a description of neighborhood where the interest points is where the interest point is, and that's going to allow us to match. So we'll discuss about this descriptor in more detail, but for now let's see the shift or scale invariant feature transform. We will discuss about the shift here. The motivation behind this development of shift is that the Harris operator is not invariant to scale, that we have already seen it in more detail, and we can also use correlation for the detection. However, it is not invariant to the rotation. So David Lowe, who developed two things for the better matching. One was to develop an interest point operator or detector that is invariant to the scale and rotation, and we have discussed about it in our previous sections, and which will be finding the maxima of difference of Gaussian both in scale and space. By doing that, we can determine the natural scale or the right scale. And another part of the shift or David Lowe's work was building a descriptor that we just discussed why we need the descriptor. That is the description of neighborhood that is more robust with respect to the variation of corresponding variations which are corresponding to the viewing conditions. So we can see here a simple example how the shift descriptor is to work. So we have got an image of truck here, and we can see these little neighborhoods or the subsections or paths of images, and these little arrows that shows the neighborhoods, and like we just extract those patches, and that shows that arrows indicates those patches that extracted from the image. And we have got some images of tires, logos, and so on. And what might be little bit harder for us to see is that we have the same truck in the another image, and the part here in the right image, like that bunch of some descriptors or the neighborhoods in the first image are found in the second image. We can see that is found, but now if we can find enough matches as here, then we can figure out the image 1 has object, and that object is also in the image 2, and it's just been rotated or translated or a little bit, maybe it's scaled. That's the idea of shift detector or shift. This is the idea of shift for doing the recognition. So if our descriptors is robust enough with respect to these transformations such as scaling, rotation, and some kind of intensity changes, we can find them in the image to the next, or we can find them in the multiple images. So the main goal of the shift is to find the matches in the next another image which is transformed using such as scaling or rotation and so on. So we'll discuss in more detail about the how we can do that in subsequent lectures. So here is the overall shift procedure for the recognition, and which was originally defined to have 4 components. The first one is finding extrema or maximums in the difference of Gaussian, which we have already discussed. And the next is detect or localize exactly where they were, and we use some method to find the key points and also determine the scale of that key points in the image, which also were discussed. And then there are 2 more steps. One is to define the orientation or orientation assignment, and we don't know how the image and the local neighbors have been transformed, and we want to know what the orientation is. And once we have the orientation, then we can find them, like we can then think of that feature with the descriptor. So here the key point is used instead of interest point, and going to use as a feature. Like we can see here it has 4 steps, and 2 of them we have already discussed, and 2 are the orientation assignment, and the another one is the key point description. And here is the picture taken again from the original shift work, and a small image on the left and the key points on the right. However, it's different from earlier. The key points here we can see the direction arrows, and these directions are going to a little local orientation that we are talking about. And next, now let's talk about the orientation assignment. Once we get the legitimate key points, we know the scale at which the key point was detected. So it is the scale invariant. The next thing is to make it rotation invariant. So we assign the orientation to each key point. A neighborhood is taken around the key point location depending on the scale, and the gradient magnitude and direction is also calculated in that region. But the idea is we're gonna build a histogram. Like we will build we estimate the gradient, and we estimate the gradient angle. And one more thing that we do here is we are going to build a histogram, and we can see the histogram here. This histogram covers 360 degree with 36 bins. And suppose that gradient direction at a certain point is 25 degree, then it will go into the bin of 20 to 29 degree bin. So and the amount that is added to the bin is proportional to the magnitude of gradient at that point. And once we have done this for all the pixels around the key point, the histogram will have a peak at some point. We can see here the peak, and the highest peak of the histogram is taken, and any peak above 80% of it is also considered to calculate the orientation, and it creates with the same location and scale but the different direction, which contributes to the stability of the matching. So here we estimate the orientation, and next is the key point descriptor. Now we will